Here is a truth that should haunt every dreamer who gazes at the stars. The universe does not block long-distance travel with a single wall. It blocks you with dozens of walls, all closing in at once. The farther you push into the cosmic void, the more systems begin failing simultaneously. Energy requirements spiral beyond any fuel supply. Time delays stretch until coordination becomes impossible. Radiation accumulates until biology surrenders. Equipment degrades until redundancy itself becomes a liability. Each constraint alone seems manageable. Together, they form a prison with bars that multiply the deeper you travel. Scientists have confirmed this compounding effect, and most people still have no idea. If you enjoy exploring and understanding the deeper truths about our universe, tap that like button and subscribe. Now, settle in and get yourself comfortable. Let's begin. Picture yourself standing at the edge of a calm lake on a summer morning. The water stretches flat as glass toward the horizon, where a small island rises perhaps 2 miles distant. You can see trees on that island, maybe a rocky shore, perhaps even a structure of some kind. The challenge seems straightforward. You could swim if you are fit enough. You could paddle a kayak with minimal effort. You could motor across in a small boat and arrive in minutes. One obstacle separates you from your destination, 2 miles of water, and multiple solutions exist for crossing it. But now imagine that same lake begins changing as you travel. With every stroke forward, the water temperature drops by a degree. Not dangerous at first, merely uncomfortable. The current strengthens against you, requiring more effort to maintain your pace. The visibility decreases as fog rolls in from nowhere. Your supplies, the water bottle you brought, the energy bars in your pocket deplete faster than expected. The air pressure shifts subtly, making each breath slightly less satisfying than the last. Individually, each change remains manageable. An experienced swimmer can handle cold water. A strong paddler can fight a current. Fog obscures but does not prevent progress. But by the time you reach the halfway point, you face not one difficulty, but 6 difficulties operating simultaneously. The cold water has numbed your limbs. The current has exhausted your reserves. The fog has disoriented your navigation. Your supplies have dwindled. Your breathing has become labored. And crucially, each problem has intensified precisely because you traveled farther from shore. The distance itself activated these challenges. Turning back now means facing them again in reverse. Pressing forward means watching them grow more severe with every meter of progress. This thought experiment captures something essential about how the universe treats long-distance travel. Distance does not simply create a larger gap to cross. Distance activates constraints that were dormant when you remained close to home. The farther you venture, the more barriers emerge from hiding. And these barriers do not politely take turns presenting themselves. They converge, overlap, and compound until the collective weight becomes unbearable. Scientists have understood individual barriers for decades. Energy requirements increase with distance. Time delays grow longer. Radiation exposure accumulates. Equipment degrades. Communication becomes impractical, measured and quantified in isolation. Propulsion engineers have devoted generations to improving how we accelerate mass through vacuum. Life support specialists have created increasingly sophisticated systems for keeping humans alive far from Earth. Communication experts have developed technologies capable of transmitting data across billions of miles. Each discipline has achieved genuine progress against its particular challenge. But the true nature of the problem reveals itself only when you examine what happens when all these constraints peak together. The universe does not defeat long-distance travel through overwhelming force applied to a single point. It defeats travel through moderate forces applied to many points simultaneously. No individual barrier is necessarily insurmountable. But when multiple barriers converge at the same distance threshold, their combined effect creates something far more formidable than any single obstacle. Consider what happens when you attempt to cross interstellar distances. The moment you commit to such a journey, you trigger a cascade of independent challenges. Your propulsion system must carry enough fuel to accelerate to useful speeds, but that fuel adds mass that requires more fuel to accelerate. This relationship is not linear. It compounds in ways that punish ambition severely. Your life support systems must function for decades or centuries without failure, but every component has a statistical likelihood of breakdown that accumulates over time. Given enough operational hours, even highly reliable systems approach certainty of failure. Your communication equipment must transmit signals across distances so vast that replies take years, but those delays mean you cannot receive help, guidance, or corrections when problems arise. You are fundamentally alone with whatever equipment and knowledge you carried at departure. Your hull must shield against radiation that accumulates with every passing moment, but shielding adds mass that increases fuel requirements. The protection you need creates the burden that slows you down. Your navigational systems must maintain accuracy across journeys lasting generations, but tiny errors compound into massive deviations over such timescales. A miscalculation of a fraction of a degree, meaningless over short distances, translates into missing your target by light years after sufficient travel. None of these constraints is insurmountable when considered alone. Engineers have designed propulsion systems that achieve remarkable efficiency. Ion drives can accelerate continuously for years. Nuclear thermal concepts promise energy densities far exceeding chemical rockets. Life support technology has kept humans alive in space for over a year, continuously aboard the International Space Station. The record grows longer with each extended mission. Communication systems have transmitted data across billions of miles. The Deep Space Network successfully maintains contact with spacecraft at the edges of our solar system. The crews of long-duration orbital flights have returned to Earth with manageable exposure levels. Navigation systems have guided spacecraft to precise targets throughout our solar system, achieving rendezvous with objects moving at tremendous velocities across vast distances. The technology exists to address each individual barrier, but the technology does not exist to address all barriers simultaneously at the scales required for long-distance travel. This distinction is crucial and often overlooked. When someone points to a breakthrough in propulsion and declares that the stars are now within reach, they have solved one equation while ignoring the dozen other equations that must balance simultaneously. When another researcher demonstrates a life support system capable of operating for extended periods, they have addressed one constraint while the others remain untouched. This is where the limits start stacking. Energy requirements do not simply add to time delays. They interact with time delays in ways that create feedback loops. Generating power for communication over vast distances requires energy that depletes fuel reserves, which extends travel time because you cannot accelerate as aggressively, which increases radiation exposure as you spend more time in the interstellar medium, which demands more shielding to protect crew and equipment, which adds mass that requires more fuel to accelerate, which extends travel time further. Each constraint feeds into others, creating amplification effects that push difficulty far beyond simple addition. The physics community has a term for systems where multiple variables interact in self-reinforcing ways: coupled systems. In a coupled system, you cannot solve one problem without affecting others. This is not merely inconvenient, it is fundamental to how such systems behave. Reducing fuel mass by using more efficient propulsion might require higher operating temperatures that accelerate equipment degradation. You solve the mass problem while creating a reliability problem. Now fees, exposures, radiation exposure, and reliability demands. You solve the energy problem while creating exposure and maintenance problems. Adding redundant systems to improve reliability increases mass, energy consumption, and complexity. You solve the reliability problem while recreating the mass and energy problems you thought you had escaped. Every solution to one constraint tightens others. This is not a failure of engineering imagination. This is how coupled systems work. The constraints are connected at fundamental levels, sharing underlying physical relationships that cannot be circumvented through clever design. Distance functions as the master variable that determines where each individual constraint falls on its severity curve. Think of each constraint as having a dial that runs from green through yellow to red. At short distances, most dials rest comfortably in green territory. At medium distances, some dials have crept into yellow while others remain green. At long distances, every dial approaches or exceeds red simultaneously, not because the universe is hostile, but because distance is the common factor that turns all the dials together. At short distances, say, low Earth orbit, most constraints remain in comfortable ranges. Energy requirements are modest relative to available technology. Chemical rockets can achieve the necessary velocities. Time delays are measured in seconds, allowing essentially real-time communication and control. Radiation exposure is significant but manageable through mission duration limits and basic shielding. Equipment reliability over mission durations of months poses engineering challenges, but not fundamental barriers. The space station requires constant maintenance, but that maintenance is possible because resupply missions arrive regularly, and crew rotations bring fresh hands and minds. Communication is essentially instantaneous from a human perception standpoint. The constraints exist at this distance, but they exist at tolerable levels that engineering can address. As distance increases toward the outer planets, each constraint begins climbing its curve. Energy requirements grow substantially. Missions to Jupiter and Saturn require years of travel, even with gravity assists that exploit planetary motion to gain velocity. Time delays extend to hours, creating meaningful gaps between command and confirmation. Controllers must anticipate problems rather than react to them. Radiation exposure becomes a serious mission consideration, particularly for any crewed mission. As the protective influence of Earth's magnetic field fades to nothing, equipment must function for years rather than months, pushing reliability requirements into new territory. Communication windows become narrow and precious, limited by orbital geometry and available antenna time. The constraints are now meaningful challenges that require careful engineering, but they remain within the reach of current or near-future technology. We have sent probes throughout the outer solar system. We have maintained communication with them. We have received their data and interpreted their findings. Push further, toward the nearest stars, and each constraint approaches or exceeds its critical threshold. Energy requirements become civilization-scale challenges. The amount of energy needed to accelerate even a modest probe to useful interstellar velocities exceeds the annual energy production of entire nations. Time delays extend to years, making real-time communication impossible and transforming every message into a historical document by the time it arrives. Radiation exposure accumulates over decades of travel through an environment filled with cosmic rays that no practical shielding can fully block. Equipment must function for centuries without repair or replacement, far exceeding any demonstrated reliability achievement in the history of technology. Navigation must maintain accuracy across distances, where the smallest angular error translates into missing the target by distances larger than our entire solar system. This is where the limit starts stacking in earnest. At interstellar distances, you do not face one barrier that technology might overcome with sufficient effort and investment. You face a convergence of barriers that all become severe at approximately the same distance threshold. This convergence is not coincidental, and understanding why it occurs reveals something profound about the structure of the challenge. The universe did not arrange this convergence deliberately. The laws of physics simply produce this effect as a natural consequence of how energy, time, and matter interact across space. Light takes time to travel because nothing can exceed a fundamental speed limit embedded in the structure of space-time itself. This is not an engineering limitation awaiting a clever workaround. It is a feature of reality as fundamental as the existence of matter. Energy requirements increase because accelerating mass requires exponentially more force at higher velocities, approaching infinity as you near light speed. Radiation accumulates because space is filled with particles and electromagnetic waves that cannot be completely blocked without adding mass that creates its own problems. Equipment degrades because all physical systems trend toward disorder over time, following thermodynamic principles that govern everything from stars to circuits. Communication delays grow because information cannot travel faster than light, meaning the same speed limit that constrains your travel also constrains your ability to coordinate with anyone behind you. Each constraint follows its own physical law. Propulsion follows the equations of momentum and energy. Radiation follows the equations of particle physics and electromagnetic interaction. Reliability follows the equations of probability and thermodynamics. Communication follows the equations of signal propagation and information theory. These are different branches of physics, studied by different specialists, expressed in different mathematical frameworks, yet all share distance as their primary driver. All grow more severe as distance increases, and all approach critical thresholds at approximately the same distance range. This shared driver creates the compounding effect that makes long-distance travel so fundamentally challenging. If energy requirements climbed steeply while time delays remained modest, engineers could focus on solving the energy problem without worrying about communication. Pour resources into propulsion research, achieve a breakthrough, and the other constraints remain manageable. If radiation exposure became severe, while equipment remained reliable, shielding could be the primary engineering focus. Develop better protection, accept the mass penalty, and other constraints accommodate. But because distance triggers all constraints together, solving any one reveals that others have simultaneously grown more severe. You cannot isolate your victories. Every step forward illuminates new obstacles that were hidden when the previous obstacle dominated your attention. The breakthrough you achieve in one domain merely hands you a clearer view of the problems waiting in other domains. The near-solar system missions humanity has accomplished demonstrate this pattern in miniature, providing a preview of what awaits at larger scales. Voyager spacecraft, launched in 1977, continue operating at the edge of interstellar space nearly 5 decades after their construction. These remarkable machines have traveled farther from Earth than any human-made object, crossing the boundary where the sun's influence gives way to the interstellar medium. But their mission profiles reveal the compounding nature of constraints, even at these comparatively modest distances. Communication with Voyager now requires enormous antenna arrays, the largest dishes humanity has built for the purpose, to detect signals weakened by distance. The spacecraft transmits with about 20 watts of power, roughly equivalent to a refrigerator light bulb, and that feeble signal spreads across billions of miles until it becomes a whisper that only the most sensitive receivers on Earth can detect. The spacecraft's power systems have degraded steadily as the radioactive decay that generates electricity has diminished according to fixed physical half-lives. Mission controllers have shut down instruments progressively, prioritizing the most valuable data collection, while abandoning capabilities that can no longer be powered. Systems that functioned perfectly at launch have gone silent, not because they failed, but because the energy to run them no longer exists. Minor course corrections have consumed propellant reserves that cannot be replenished. Every adjustment to Voyager's trajectory, no matter how small, drew from a fixed supply of hydrazine that depleted with each use. Today, what remains must be rationed against future needs that cannot be fully anticipated. The time delay between sending a command and receiving confirmation now exceeds 40 hours, nearly 2 full Earth days. Controllers must commit to actions and then wait, unable to observe results, unable to abort if something goes wrong, before learning whether their commands executed successfully, and Voyager travels at a pace that would require tens of thousands of years to reach the nearest star system. The spacecraft represents humanity's most successful long-distance mission, a genuine triumph of engineering and determination, yet it illustrates how constraints accumulate even when each individual constraint remains technically manageable. Voyager succeeded because its mission requirements remained within the zone, where constraints, though challenging, had not yet converged into impossibility. The power systems lasted long enough for the core mission. The communication technology proved sufficient for the distances involved. The radiation exposure remained tolerable for its electronic components, which faced different thresholds than biological systems would. The time delays were manageable for a mission requiring limited real-time guidance. Voyager mostly follows its programmed trajectory, with only occasional interventions from Earth. But scaling this success to truly interstellar distances would require overcoming not one constraint, but all constraints that Voyager encountered, each intensified by orders of magnitude. The power systems would need to function for centuries rather than decades. The communication system would need to bridge distances measured in light years rather than light hours. The radiation exposure would accumulate across journey times, measured in human generations. The time delays would extend from inconvenient to functionally infinite from an operational standpoint. Voyager teaches us what the constraints look like when they begin to converge. Interstellar distances show what they look like when the convergence is complete. The engineering approach that works within our solar system, identifying the primary constraint and dedicating resources to overcome it, breaks down when constraints converge. Within the solar system, missions can often identify a single dominant challenge. Getting to orbit requires solving the energy problem of escaping Earth's gravity well. Engineers focused on that problem and developed rockets capable of achieving the necessary velocities. Reaching distant planets requires solving the timing problem of orbital mechanics. Calculating trajectories that exploit gravity assists in arrival windows. Mission planners focused on that problem and created techniques for threading spacecraft through the solar system with remarkable precision. Surviving on planetary surfaces requires solving the environmental problem of hostile conditions. Designers focused on that problem and built rovers that function in conditions no human could tolerate, unprotected. These singular challenges yield to focused engineering effort. Identify the bottleneck, concentrate resources, achieve the breakthrough, and proceed. This approach has driven the entire history of spaceflight, producing steady advances as each generation of engineers tackles the dominant constraint of their era. But long-distance travel presents no singular challenge to overcome. The moment you achieve the energy breakthrough needed for interstellar propulsion, you discover that your radiation shielding has become inadequate for the extended exposure time your propulsion system requires. Faster is not simply better. Faster changes the radiation environment you must survive, because higher velocities mean more energetic impacts with interstellar particles. The moment you develop shielding sufficient for long-duration travel, you find that its mass has increased your energy requirements beyond what your breakthrough propulsion can deliver. The protection solution has recreated the propulsion problem in a new form. The moment you miniaturize systems to reduce mass, you discover that component reliability over extended timescales has dropped below acceptable thresholds. Smaller components often mean more vulnerable components, with less margin for error and fewer pathways for redundancy. This is not pessimism but physics. The constraints are real, measured, and confirmed by decades of space exploration experience. Every long-duration mission has taught us something about how challenges accumulate over time and distance. Every probe that has fallen silent has demonstrated the limits of reliability. Every communication delay has shown us what it means to operate without real-time guidance. The data is extensive, consistent, and sobering, and the constraints are coupled in ways that create barriers far more formidable than any individual obstacle. Distance doesn't add one problem, it activates many problems at once. This principle applies not just across different categories of constraint, but within categories as well. Energy alone creates multiple interacting challenges. Time alone creates multiple interacting challenges. The categories themselves interact with each other. The result is a web of constraints so densely interconnected that pulling on any thread tightens others. Understanding this architecture of barriers changes how we must think about the challenge of long-distance travel. The question is not which constraint will prove most difficult to overcome. Asking that question assumes the constraints can be addressed sequentially, that solving the hardest one opens the door to addressing the others. The real question is whether the convergence of constraints at interstellar distances represents a fundamental limit that no technology can circumvent. Not because any single barrier is insurmountable, but because too many barriers become severe at the same time. The farther you go, the more systems fail at once. This is not a failure of preparation or planning. This is the nature of how distance interacts with physical law. The constraints do not care whether you have solved other constraints. They respond to distance independently, growing severe on their own schedules, reaching critical thresholds that happen to cluster at approximately the same range. The clustering is not conspiracy, it is consequence. What follows examines how energy requirements alone create multiple stacking constraints, demonstrating that even within a single category of challenge, the compounding effect manifests with full force. Distance does not add one energy problem. It activates many energy problems simultaneously. Propulsion demands, communication power, life support loads, thermal management requirements, radiation shielding energy costs, each feeding into the others, until energy itself becomes a barrier that multiplies rather than adds to mission difficulty. The architecture of barriers begins with the most fundamental resource of all, and even there, the stacking effect reveals itself in full complexity. Energy is the currency of space travel. Every function a spacecraft performs: acceleration, communication, life support, computation, radiation shielding, thermal regulation, demands energy drawn from finite reserves. There is no credit in space, no borrowing against future production, no renewable source that replenishes automatically as you travel farther from the sun. What you spend is gone forever, and the farther you travel, the more you must spend on every category of operation simultaneously. Within the inner solar system, energy constraints remain manageable because distances are short, sunlight is abundant, and missions are brief enough that reserves can be calculated with confidence. A mission to Mars requires substantial energy for the journey, but the Sun still provides usable power at Martian distance. A mission to the outer planets stretches solar collection to its limits, but radioactive decay can substitute where sunlight fails. The constraints exist, but they exist at levels where engineering solutions remain viable. But as distance increases beyond our solar neighborhood, energy transforms from a resource to be managed into a barrier that compounds upon itself. The transformation is not gradual, it accelerates. Each additional light year of distance activates new energy demands while intensifying existing ones. The relationship between distance and energy requirement is not a gentle slope, but a steepening curve that eventually approaches vertical. The most obvious energy constraint involves propulsion. Moving any mass through space requires applying force over time. This is fundamental physics, unchanged since Newton first described it 3 centuries ago. The faster you want to travel, the more energy you must expend. But this relationship is not linear. It is exponential in its practical effects. Doubling your velocity does not simply double your fuel consumption. It increases consumption by a factor far greater because you must accelerate not only your payload but also the fuel you have not yet burned. This creates the tyranny of the rocket equation, a mathematical relationship that has haunted spacecraft designers since the earliest days of spaceflight. To carry enough fuel to reach high velocities, you need more fuel to accelerate that fuel. But carrying more fuel means more mass, which requires even more fuel to accelerate. The equation spirals upward with punishing speed. For chemical rockets, achieving velocity changes beyond a certain threshold requires fuel masses that exceed practical limits by orders of magnitude. The fuel tank becomes larger than the spacecraft, then larger than a building, then larger than a city. Eventually, the fuel requirement exceeds the mass of available planets. Engineers have developed clever approaches to this fundamental challenge. Ion drives provide thrust far more efficiently than chemical rockets by accelerating small amounts of propellant to very high velocities. Rather than explosive chemical reactions that throw mass away at moderate speeds, ion drives use electromagnetic fields to accelerate individual atoms to velocities approaching 100,000 miles per hour. The thrust is tiny. You could overpower an ion drive by blowing on it, but applied continuously over months or years, that tiny thrust accumulates into substantial velocity changes while consuming far less propellant than chemical alternatives. Nuclear propulsion concepts promise to deliver more energy per unit mass than any chemical reaction can achieve. Nuclear fission releases roughly 1 million times more energy per kilogram than the best chemical fuels. Nuclear fusion, if it could be harnessed for propulsion, would release even more. These are not marginal improvements, but revolutionary leaps in energy density. A spacecraft carrying nuclear fuel could theoretically achieve velocities impossible for chemical rockets without requiring fuel masses that exceed comprehension. Solar sails exploit the pressure of light itself to provide continuous acceleration without consuming any propellant at all. Photons carry momentum despite having no mass, and when they bounce off a reflective surface, they transfer that momentum to whatever they strike. A sufficiently large and lightweight sail could harvest enough photon momentum to accelerate a spacecraft, gradually but indefinitely, requiring no onboard fuel supply whatsoever. Several experimental solar sail missions have demonstrated the principle works. Each approach represents genuine progress in propulsion efficiency. Ion drives have powered missions to asteroids and comets. Nuclear thermal designs have been tested and validated. Solar sails have deployed successfully in space. These are not theoretical concepts, but demonstrated technologies that continue improving with each generation. But efficiency improvements cannot eliminate the fundamental constraint. They can only push back its threshold. Even a perfectly efficient propulsion system, one that converts every joule of input energy into kinetic energy of motion with zero waste, must contend with the fact that energy must come from somewhere. Chemical fuels carry their energy locked in chemical bonds between atoms. Nuclear fuels carry their energy locked in atomic nuclei themselves. Solar collection systems depend on proximity to a star whose light provides the energy. Each source imposes its own limitations that compound with other constraints, and no source provides infinite energy in finite mass. Consider a spacecraft attempting to reach a distant target using nuclear propulsion, currently the most energetic practical option under serious study. Nuclear reactions release millions of times more energy per unit mass than chemical reactions. This improvement is real and significant. It represents one of the largest energy density improvements available in known physics. But nuclear fuel still has mass. Uranium and plutonium are among the densest elements in nature, and carrying enough for an interstellar journey means carrying substantial tonnage regardless of the energy it contains. Reactors to harness that fuel have mass. You cannot simply ignite nuclear material and direct the explosion. Not if you want controlled thrust over extended periods. Reactors require containment vessels, moderators, control systems, heat exchangers, and all the supporting infrastructure that transforms raw nuclear energy into usable thrust. This infrastructure weighs thousands of kilograms in current designs and would weigh substantially more in designs scaled for interstellar missions. Shielding to protect crew and equipment from reactor radiation has mass. Nuclear reactions produce intense radiation that would kill human beings within hours of unshielded exposure and would degrade electronic components over longer timescales. The shielding required to create safe operating zones around a nuclear propulsion system adds tonnage that compounds the propulsion challenge. Heat rejection systems to manage reactor thermal output have mass. Nuclear reactions generate enormous heat, and in the vacuum of space, that heat can only be radiated away through large surface areas that add structural mass to the spacecraft. Each gram of mass you add to exploit nuclear energy's advantages requires more nuclear fuel to accelerate, which adds mass, which requires more fuel. The rocket equation's tyranny applies regardless of fuel type. Nuclear propulsion pushes the threshold back substantially compared to chemical rockets, but it does not eliminate the fundamental relationship between mass and energy that governs all propulsion. This is where the limits start stacking within the energy domain alone. Propulsion energy is not a single constraint, but a cluster of interconnected constraints wearing a single name. Fuel mass constraints interact with reactor mass constraints, which interact with shielding mass constraints, which interact with thermal management constraints. Each constraint responds to the others. Solving one creates demands on others. The system is coupled at fundamental levels, and coupled systems resist optimization because every improvement in one area imposes costs in others. You might imagine eliminating crew to reduce shielding requirements, but crewless spacecraft still carry electronics that suffer radiation damage. You might imagine eliminating reactor shielding entirely and accepting some electronics degradation, but radiation damage accelerates component failure that compromises mission success. You might imagine miniaturizing reactors to reduce overall mass, but smaller reactors produce less power, requiring longer acceleration phases that extend mission duration and create their own complications. But propulsion represents only one category of energy demand, and long-distance travel activates all categories simultaneously. Communication across vast distances requires enormous power that propulsion calculations rarely include. Radio signals spread as they travel, following the inverse square law that governs all radiation propagating through space. Double the distance, and you need 4 times the power to maintain the same signal strength at the receiver. Triple the distance, and you need 9 times the power. This relationship is not engineering limitation but geometry. The same energy spread across a larger sphere means less energy per unit area at every point on that sphere. At interstellar distances, this relationship becomes devastating. The nearest star system lies approximately 4 light-years from Earth. A radio signal transmitted toward that star would spread across a sphere with a surface area roughly 400,000 trillion times larger than the antenna that transmitted it. Even the most sensitive receivers would need extraordinarily powerful transmissions to detect any signal at all. A signal strong enough to be reliably detected from a nearby star system would require transmission power exceeding the output of major power plants, not for a brief burst but sustained for the duration of the message, repeated as often as communication is desired. And that power must come from onboard energy reserves that are simultaneously being depleted by propulsion, life support, and dozens of other systems. Every watt devoted to communication is a watt unavailable for other purposes. Every joule transmitted toward Earth is a joule that cannot be used to maintain spacecraft operations. Spacecraft designers have developed techniques to manage communication power requirements. Highly directional antennas focus signal energy toward receivers rather than broadcasting in all directions. A dish antenna concentrates transmission power into a narrow beam, dramatically increasing effective signal strength toward the target, while wasting nothing on empty space. The deep space network that communicates with distant probes uses enormous dish antennas for exactly this reason, both to transmit stronger signals and to collect weaker signals more effectively. Efficient encoding schemes extract more information from weaker signals by building redundancy into transmissions. If some bits are corrupted by noise, the encoding allows reconstruction of the original message. Data compression reduces the number of bits that must be transmitted to convey a given amount of information. Error correction and compression together can stretch communication capability substantially beyond what raw signal strength alone would suggest. But these approaches cannot eliminate the inverse square law. They can only extend the distance at which communication remains practical, and extending that distance requires equipment mass, larger antennas, more sophisticated processors, more capable transmitters, and energy consumption that compound with other constraints. The antenna that enables communication with a distant star weighs something. The transmitter that powers it draws electricity. The computer that encodes and decodes messages consumes energy continuously. Each improvement in communication capability exacts payment in mass and power that affects every other system. Life support systems present their own energy demands that grow with mission duration rather than distance directly. Though distance and duration are inextricably linked for any practical mission, maintaining habitable temperature ranges requires energy for heating in the cold of deep space, where ambient temperature approaches absolute zero and heat radiates away continuously from any warm surface. Cooling is equally necessary when equipment generates waste heat that cannot be allowed to accumulate in crew areas. The same spacecraft may require heating for crew quarters and cooling for engine compartments simultaneously, demanding energy for both functions. Recycling atmosphere and water requires energy to power chemical and mechanical processes that separate useful substances from waste. Human beings consume oxygen and produce carbon dioxide. They consume water and produce urine. They consume food and produce solid waste. Without recycling, a long-duration mission would need to carry all consumables for the entire journey, plus safety margins, masses that become prohibitive for voyages lasting years or decades. But recycling is not free. Every chemical separation, every filtration process, every purification step requires energy input. The laws of thermodynamics guarantee that no recycling process can be perfectly efficient. Some energy is lost at each step, accumulating into significant demands over extended operations. Producing food, if mission duration exceeds what stored supplies can provide, requires energy for lighting, temperature control, atmosphere management, and processing. Plants require light to photosynthesize. They require specific temperature ranges to grow. They require carbon dioxide and water in appropriate quantities. Maintaining food production systems adds energy demands on top of the energy demands of keeping crew alive to eat the food. Maintaining artificial gravity through rotation, if that proves necessary for long-term crew health, requires energy to establish rotation and maintain it against any forces that might slow the spinning habitat. Each life support function can be made more efficient through clever engineering. Closed-loop recycling systems can reduce consumable requirements to tiny fractions of open-loop alternatives. The International Space Station already demonstrates many of these technologies, recycling water and atmosphere with impressive efficiency. Better insulation can reduce thermal management loads by slowing heat transfer in both directions. More efficient lighting can reduce food production energy costs, with LED systems already providing dramatic improvements over older technologies. But efficiency improvements have limits imposed by thermodynamics. No process can be perfectly efficient. Every energy conversion loses some energy to heat that must itself be managed. The laws of physics establish floors below which efficiency cannot fall regardless of engineering cleverness. Over mission durations measured in decades, even small inefficiencies accumulate into significant energy demands that cannot be engineered away. Radiation shielding presents a particularly insidious energy challenge because it offers a direct choice between mass and power. Space is filled with high-energy particles from cosmic sources and stellar events. Galactic cosmic rays have traveled for millions of years from distant supernovae and other cataclysmic events. Solar particle events erupt from the Sun during magnetic disturbances. These particles carry enough energy to penetrate spacecraft hulls, damage biological tissues, and disrupt electronic components. They cannot be entirely avoided. They fill the space through which any interstellar mission must travel. Protecting against radiation requires either mass in the form of physical shielding that absorbs or deflects particles, or energy in the form of electromagnetic fields that deflect charged particles before they reach vulnerable targets. Physical shielding adds mass that increases propulsion energy requirements. A spacecraft carrying sufficient water, or polyethylene, or other shielding material to protect crew from cosmic rays over years of exposure would weigh substantially more than an unshielded spacecraft, requiring more propulsion energy to accelerate. Electromagnetic shielding requires continuous power to maintain the magnetic fields, depleting energy reserves throughout the mission. The amount of shielding required increases with exposure time. A brief transit through a radiation-intensive region a few days or weeks might be survivable with modest protection. Human beings have evolved with radiation repair mechanisms that can address limited damage. But an extended journey lasting years or decades requires far more robust shielding because damage accumulates faster than biology can repair it. Cancer risk increases with cumulative exposure. Cognitive effects emerge with sustained radiation. Electronic components accumulate errors that eventually cause failures, but adding shielding adds mass or energy consumption, which affects propulsion requirements in ways that extend travel time if energy must be conserved for propulsion, which increases radiation exposure because more time passes in the radiation environment, which demands more shielding to maintain protection levels. The constraint feeds back on itself in a vicious cycle, where the solution worsens the problem that motivated it. Distance doesn't add one problem, it activates many at once. The radiation challenge alone demonstrates this compounding nature. More distance means more travel time, means more exposure, means more shielding, means more mass, means more energy, means potentially more travel time. Each element of the chain connects to others, and pulling on any link tightens the entire structure. Equipment operation presents yet another energy demand category that scales with mission complexity. Computers require power for processing. Even the most efficient processors consume electricity to perform calculations, and that consumption continues as long as the computers operate. Sensors require power for detection and analysis. Cameras need electricity to capture images. Spectrometers need power to analyze light. Communication receivers need energy to detect and amplify signals. Motors and actuators require power for mechanical operations, moving antennas, adjusting solar panels, operating airlocks, controlling valves. The complexity that enables spacecraft to function autonomously over long durations, a necessity when communication delays make real-time control from Earth impossible, requires sophisticated systems that consume energy continuously. A spacecraft, capable of navigating independently, diagnosing its own failures, managing life support without human oversight, and making decisions about resource allocation, needs substantial computational capability running around the clock. Modern spacecraft have achieved remarkable reductions in computing power requirements compared to earlier generations. The computer that guided Apollo to the moon was less capable than a modern digital watch. Today's spacecraft carry processors thousands of times more powerful while consuming fractions of the power. This improvement trend continues with each generation of electronics, but processing demands also increase with autonomous operation requirements. A spacecraft that must make independent navigation decisions cannot simply run a pre-programmed flight plan. It must sense its environment, analyze what it detects, compare that to expectations, calculate appropriate responses, and execute those responses while monitoring for unexpected results. A spacecraft that must diagnose and respond to equipment failures needs diagnostic software, failure libraries, decision algorithms, and actuation systems to implement repairs or workarounds. A spacecraft that must manage complex life support systems needs continuous monitoring, predictive modeling, resource allocation algorithms, and intervention capabilities. That capability requires energy that must come from finite reserves that deplete throughout the mission. The processing power needed for full autonomy far exceeds what simple trajectory following requires. The power consumption accumulates continuously for the duration of the mission. Thermal management represents a constraint that interacts with nearly every other energy demand, creating feedback loops within feedback loops. In the vacuum of space, heat can only be radiated away. There is no air to carry it through convection, no water to conduct it away through contact. Equipment generates heat during operation. Every processor, every motor, every actuator converts some electrical energy into waste heat. Reactors generate enormous amounts of heat during power production. Life support systems must maintain temperature ranges suitable for biology, which means rejecting heat when things run too warm and retaining heat when things run too cold. Rejecting unwanted heat requires radiators large surface areas that glow in infrared as they shed thermal energy to space. But radiators have mass that adds to propulsion requirements. Radiators require pumping systems to circulate coolant, and those pumps consume electricity. Retaining needed heat requires insulation and active heating systems, both of which consume resources. Managing thermal loads requires continuous attention and continuous energy expenditure. The thermal challenge compounds with nearly every other system. More powerful computers generate more waste heat. Larger reactors require larger radiators. More life support capacity means more thermal load in both directions. Power generation itself becomes a compounding constraint at interstellar distances. Solar panels, the workhorse power source for inner solar system missions, become useless beyond a certain distance from any star. The sun's energy diminishes with the square of distance, the same inverse square law that governs communication signals. By the orbit of Mars, solar intensity has dropped to roughly 43% of its value at Earth's distance. By Jupiter, it has dropped to roughly 4%. By Neptune, it has dropped to roughly 0.1% less than 1,000th the intensity available at Earth. Beyond our solar system, where interstellar missions must travel, solar panels become dead weight. They produce effectively zero power while adding mass that propulsion systems must accelerate. Any interstellar mission must carry alternative power sources that function without sunlight. Nuclear power systems provide an alternative that does not depend on stellar proximity. Radioisotope thermal generators have powered deep space missions for decades, converting the heat from radioactive decay directly into electricity through thermocouples. Voyager spacecraft still operate on power from radioisotope generators launched nearly 5 decades ago. This technology is proven, reliable, and independent of distance from any star. But these systems decay over time as their radioactive fuel diminishes according to fixed half-lives that no engineering can alter. Plutonium-238, the isotope most commonly used, has a half-life of roughly 87 years. A generator providing 100 watts at launch will provide roughly 50 watts after 87 years. It will provide roughly 25 watts after 174 years. The power curve is fixed by nuclear physics. Mission planners must either launch with excess capacity that goes unused early in the mission, adding mass and complexity that propulsion must carry, or accept diminishing power availability as the mission progresses. For interstellar missions lasting centuries, the power available at arrival might be a tiny fraction of the power available at departure. Fission reactors can provide larger power outputs than radioisotope generators by actively managing nuclear chain reactions rather than relying on natural decay. Reactors have been tested in space and could theoretically provide megawatts of power for extended periods. But reactors require fuel that is consumed during operation, demanding that sufficient fuel be carried for the entire mission. Reactors require maintenance that becomes impossible when no human hands can reach them. Control rods wear. Coolant systems degrade. Structural components fatigue. Reactors require complex control systems that add failure modes to already complicated spacecraft. Fusion power, often proposed as the ultimate solution to space energy challenges, remains decades away from practical implementation. despite more than 70 years of intensive research since the first concepts emerged. Even if fusion power were achieved, reactors would have mass, fuel requirements, maintenance needs, and thermal management demands that would compound with other constraints. Fusion would push thresholds back substantially, it would not eliminate them. Energy storage presents its own category of compounding limits that interact with both generation and consumption. Batteries store energy in chemical bonds, but have limited energy density compared to fuels roughly 100 times less energy per kilogram than gasoline, thousands of times less than nuclear fuel. Batteries degrade over charge-discharge cycles, losing capacity progressively until they become useless. Batteries have temperature requirements that add thermal management complexity. Capacitors store energy in electric fields but discharge rapidly and cannot maintain power over extended periods. They excel at providing brief bursts of high power, but cannot sustain continuous loads. Flywheels store energy in rotational momentum but require bearings that wear and fail over time. Each storage technology has characteristics that make it suitable for some applications but inadequate for others. No storage technology eliminates the fundamental constraint that energy stored has mass, and mass requires energy to move. The spacecraft designer attempting to create a vehicle for long-distance travel faces not an engineering challenge, but an optimization impossibility. Every design decision that improves one energy parameter degrades others. Increasing propulsion efficiency might require higher operating temperatures that accelerate component failure rates. Increasing power generation capacity adds mass that increases propulsion demands. Reducing mass through miniaturization increases vulnerability to radiation damage, because smaller components have less material to absorb particle impacts. Extending fuel reserves extends mission duration, which increases life support energy requirements. The farther you go, the more systems fail at once, and in the energy domain, systems fail by demanding more than any reasonable design can provide simultaneously. Propulsion needs conflict with communication needs. Power generation needs conflict with shielding needs. Thermal management needs conflict with mass reduction needs. The optimization space that works for inner solar system missions, where constraints are loose enough that acceptable solutions exist, collapses into impossibility at interstellar distances where all constraints tighten together. At interstellar distances, these trade-offs do not merely complicate engineering, they appear to close off solution space entirely. The energy required for propulsion alone, even with optimistic assumptions about future technology, approaches levels that would require consuming substantial fractions of civilization's total energy output to launch a single mission. Add communication power requirements, life support loads, radiation shielding energy demands, thermal management needs, computing requirements, and all the other categories of energy consumption, and the total grows beyond any reasonable projection of technological capability. This is not pessimism but mathematics. The calculations have been performed repeatedly by researchers hoping to find pathways to the stars. Each analysis concludes that energy requirements at interstellar scales exceed current or foreseeable capabilities by factors so large that incremental improvements cannot bridge the gap. Revolutionary breakthroughs in multiple energy technologies simultaneously might push the threshold back far enough to attempt interstellar missions. But even revolutionary breakthroughs must contend with the compounding relationships that cause constraints to interact and reinforce each other. The energy constraints described here represent only one category of limits that compound as distance increases. The following section examines how time transforms from a neutral medium into an active enemy, how reliability decays, how maintenance becomes impossible, how communication delays destroy coordination, and how the very complexity designed to ensure survival becomes the mechanism of breakdown. But even before considering these additional categories, energy alone demonstrates the compounding nature of barriers to long-distance travel. The universe does not present a single energy wall to be overcome through propulsion breakthroughs or power generation miracles. It presents a convergence of energy demands that all grow severe together, each one feeding into others, creating barriers that multiply rather than add as distance increases. Solving propulsion energy does not solve communication energy. Solving power generation does not solve energy storage. Solving any one component merely reveals how tightly it was connected to every other component, how every thread in the web pulls on every other thread. This is where the limits start stacking, and in the energy domain, the stack grows tall before we have even considered what time does to every system that energy must power. Time is not neutral. We experience time as a passive medium through which events unfold, a backdrop against which life happens. Clocks tick, calendars turn, seasons change, but time itself seems to do nothing. It merely passes while other forces act. This intuition, forged through daily experience on Earth where repairs are possible and replacements available, fails catastrophically when applied to long-distance space travel. In the void between stars, time becomes an active adversary. Every second that passes represents another opportunity for something to fail, another interval of radiation damage, another moment when help grows more distant. Time does not merely pass during interstellar journeys. Time attacks. Every manufactured component has a failure probability. This is not pessimism or poor engineering. It is fundamental to how physical systems work. No material is perfectly uniform. No assembly process achieves perfect precision. No operating environment remains perfectly stable. These imperfections, invisible at human timescales, accumulate into certainties over extended operation. Such reliability would be considered exceptional by any engineering standard. For a mission lasting days or weeks, this failure probability provides enormous safety margins. The chance of failure during a 2-week mission is roughly 1 in 3,000 excellent odds by any measure, but long-distance travel does not operate on timescales of days or weeks. Journeys to nearby stars, even at velocities far exceeding any current capability, would require decades at minimum. More realistic propulsion scenarios extend timescales to centuries. Over 100 years of continuous operation, that 1 in a million hourly failure probability transforms through relentless accumulation. 100 years contains approximately 876,000 hours. Multiply those hours by the failure probability, and the mathematics becomes uncomfortable. That exceptionally reliable component now faces odds of failure approaching certainty. And spacecraft contain not one component, but thousands. Each component carries its own failure probability. The spacecraft as a whole faces the combined failure probabilities of every part working together, which means the system fails when any critical component fails. For complex systems with thousands of critical components, the mathematics of accumulated probability creates timelines where failure transitions from unlikely to inevitable far faster than intuition suggests. Engineers address reliability concerns through redundancy. This approach has proven spectacularly effective for shorter duration missions. If one component might fail, include 2 or 3 backups. If one system might malfunction, design alternative pathways to achieve the same function. The Space Shuttle flew with multiple redundant flight computers, any one of which could control the vehicle if others failed. The International Space Station maintains backup systems for life support, power distribution, and communication. Mars rovers carry spare mechanisms for critical functions like wheel motors and instrument deployment. When primary systems fail, and they do fail, regularly backup systems activate and missions continue. Redundancy works when backup systems can be activated quickly after primary failures are detected, and when the overall mission duration remains short enough that backup systems themselves retain high reliability. A backup computer sitting idle for 6 months remains almost as reliable as it was at launch. A backup computer sitting idle for 60 years has accumulated the same degradation mechanisms that doomed the primary system, just delayed by whatever interval separated their activation. This is where the limits start stacking in the temporal domain. Redundancy, the standard engineering solution to reliability concerns becomes a liability rather than an asset. When repair is impossible and mission duration exceeds expected component lifetimes, adding backup systems adds mass that increases propulsion requirements, which extends travel time, which increases the duration over which backup systems must remain functional. The solution intended to improve reliability actually extends the timeline over which reliability must be maintained. Consider the mathematics more carefully. If your primary system fails in year 5 of a century-long mission, your backup system must then operate for 95 years, facing the same reliability challenges that doomed the primary system. Starting from a baseline that has already accumulated 5 years of dormant degradation, backup systems are not frozen in time while they wait. They experience thermal cycling as the spacecraft rotates through heating and cooling phases. They absorb radiation that damages their components. Their lubricants slowly migrate, evaporate, or break down chemically. Their seals deteriorate. Their electrical connections corrode at microscopic levels. When the backup finally activates, it does not begin fresh. It begins already aged, already degraded, already partway toward its own failure. The redundancy that seemed like insurance has become another entry in the failure probability calculation, another component whose reliability accumulates toward breakdown. The challenge intensifies because adding more backups does not escape the mathematics, it merely changes the coefficients. 3 redundant systems last longer than 2, on average. 10 redundant systems last longer than 3. But each additional backup adds mass, complexity, and its own failure modes. And no finite number of backups survives infinite operation. Eventually, all redundant paths fail. The question becomes whether mission duration exceeds the timeline on which all redundancy exhausts itself. For interstellar missions, the answer appears to be yes. No demonstrated technology maintains reliability across the timescales involved. The longest operating spacecraft in history, the Voyager probes, have functioned for roughly 5 decades. This represents a genuine triumph of engineering, but 5 decades is less than 1/10 the minimum duration projected for interstellar travel. And Voyager's systems have degraded substantially over even this shorter interval. Instruments have been shut down. Capabilities have been lost. The spacecraft that exists today is a diminished version of what launched in 1977. Scaling Voyager's success to interstellar timescales would require not incremental improvement, but fundamental transformation in how we think about reliability. Components would need to function for periods exceeding the entire history of human technology. No such capability exists or appears achievable through extensions of current approaches. Mechanical systems present particularly acute temporal challenges because they involve physical contact between moving parts. Bearings wear through rotation as surfaces slide against each other, removing microscopic amounts of material with each cycle. Seals deteriorate through thermal cycling as materials expand and contract at different rates, creating gaps that grow imperceptibly wider over thousands of repetitions. Lubricants migrate away from contact surfaces, evaporate into vacuum, or break down chemically through oxidation and thermal stress. Springs lose tension through metal fatigue as crystalline structures slowly reorganize under constant stress. Connectors corrode through electrochemical processes that operate continuously at any temperature above absolute zero. Each degradation mechanism operates on its own timescale, determined by materials, design, and operating conditions. Some mechanisms complete their damage in years, others require decades, but all share the property that they progress continuously and cannot be reversed without intervention. A bearing that has worn halfway to failure cannot unwear itself. A seal that has cracked cannot heal. A spring that has lost tension cannot regain it through rest. Within our experience on Earth and in near-Earth space, we address mechanical degradation through maintenance. We inspect components for wear. We replace parts before they fail. We refresh lubricants tighten loose connections, swap out degraded seals. This maintenance model assumes access to replacement parts, diagnostic tools, skilled personnel, and time windows where equipment can be taken offline for service. Aircraft are inspected after every flight. Vehicles receive scheduled maintenance at specified intervals. Industrial equipment has maintenance programs that track component age and replace parts proactively. None of these assumptions holds for long-distance travel. A spacecraft bound for distant destinations cannot carry replacement parts for every component that might fail over a century of operation. The mass budget simply does not permit it. Carrying sufficient spares would multiply spacecraft mass many times over, creating propulsion requirements that cascade through every other constraint. Even if spare parts could be carried, installation requires tools, workspace, and expertise that may not be available. A human crew might perform some repairs, but crew members age, sicken, and die over century-long journeys. An uncrewed spacecraft has no hands to turn wrenches or eyes to inspect wear patterns. The farther you go, the more systems fail at once, and the fewer resources remain available for addressing those failures. Distance translates directly into isolation. Isolation translates directly into inability to repair. Electronic systems present different but equally challenging temporal constraints. Unlike mechanical systems that wear through physical contact, electronics degrade through subtler processes that operate at atomic and molecular scales. Semiconductors accumulate radiation damage as high-energy particles displace atoms from their crystalline positions, creating defects that alter electrical properties. Each particle impact is insignificant. Billions of impacts over years of operation progressively degrade performance. Memory cells develop errors as cosmic rays flip stored bits and as charge gradually leaks from storage capacitors. Error-correcting codes can compensate for limited corruption, but correction capability has limits. Eventually, accumulated errors exceed what correction can handle, and stored data becomes unreliable. Processors slow as transistors degrade through quantum tunneling effects that increase leakage current and reduce switching speed. The processor that executed 1 billion operations per second at launch might execute only millions per second after decades of degradation. Software presents its own category of temporal vulnerability. Programs do not wear out in the physical sense. The same code executes identically, regardless of how many times it runs. But software interacts with hardware that changes over time. As memory cells corrupt, software may execute incorrectly even if the code itself remains intact. As sensors degrade, software receives inputs that diverge from calibrated expectations. As processors slow, timing-dependent operations may fail in subtle ways. Software can also develop pathological behaviors through gradual accumulation of corrupted state. A variable that should never exceed a certain value might increment past its limit through memory errors, causing cascading failures through code that assumed the limit would hold. These failures may not manifest immediately. They may lurk for years before some combination of conditions triggers visible malfunction. Unlike mechanical failures, which often announce themselves through noise, vibration, or obvious malfunction, electronic degradation can be silent and gradual until catastrophic failure occurs. A system may appear to function normally while actually operating on margins that have shrunk dangerously thin. Then, without warning, it crosses some threshold and fails completely. This silent degradation makes monitoring difficult and prediction unreliable. Radiation damage deserves particular attention because it accumulates continuously throughout any journey through space and cannot be entirely prevented regardless of shielding. Even within our solar system, spacecraft experience constant bombardment by particles from the Sun and from cosmic sources beyond the solar system. These particles carry energies spanning enormous ranges, from modest solar wind to ultra-high energy cosmic rays that pack the punch of a fastball into a single proton. Shielding reduces but cannot eliminate this exposure. Some particles are simply too energetic to stop with any practical amount of material. A cosmic ray with sufficient energy can penetrate meters of lead. No spacecraft can carry such shielding without becoming too massive to launch. The practical result is that some radiation exposure is unavoidable for any mission, and exposure accumulates linearly with time spent in space. Biological systems are particularly vulnerable to radiation effects. Human cells accumulate damage as particles ionize molecules, break DNA strands, and disrupt cellular machinery. Repair mechanisms operate continuously to fix this damage, and they succeed most of the time. But repair is not perfect, and some damage evades correction. Over mission durations of decades, even modest radiation levels accumulate into significant biological harm. Cancer risk increases. Cardiovascular damage develops. Cognitive function may decline as neurons accumulate injury. The exposure limits established for astronauts reflect this accumulation. An astronaut who has reached their lifetime exposure limit cannot fly again regardless of how healthy they appear, because their accumulated damage has raised long-term health risks to unacceptable levels. For interstellar missions lasting far longer than any astronaut career, these limits would be exceeded many times over even with aggressive shielding. But radiation also damages non-biological systems in ways that compound with other reliability constraints. Semiconductor devices become more error-prone, as particle impacts create defects in crystal structures. Solar cells lose efficiency as radiation damages the photovoltaic junctions that convert light to electricity. Optical systems cloud, as radiation degrades transparent materials through molecular bond disruption. Structural materials become brittle as radiation damage accumulates in polymer chains and metallic crystalline structures. The systems designed to enable long-duration missions are themselves vulnerable to the environment they must traverse. There is no escaping this vulnerability. It can only be managed, and management has costs and limits. Communication delays introduce another category of temporal constraint that compounds with reliability challenges rather than operating independently. Light requires approximately 4 years to travel to the nearest star system, and 4 years to return. This is not an engineering limitation, but a fundamental feature of space-time. Nothing travels faster than light, including information. Any message sent to a spacecraft at interstellar distances would take years to arrive, and any reply would take additional years to return. A complete round-trip communication cycle spans nearly a decade. During that decade, everything changes. Equipment fails. Trajectories deviate. Emergencies arise. Conditions evolve in ways that could not be anticipated when the original message was sent. By the time a reply arrives from Earth, the question it answers may no longer be relevant. The situation it addresses may have resolved or worsened beyond the advice's applicability. This communication lag destroys the operational model that has enabled successful space exploration within our solar system. Missions to Mars, which experience communication delays of up to 24 minutes each way, already strain the limits of remote operation. Controllers cannot joystick rovers in real time. They must send sequences of commands and wait, hoping conditions remain stable long enough for execution. If something unexpected happens, a rock that was not visible in orbital imagery, a slope steeper than terrain models suggested, the rover must handle it autonomously, or sit paralyzed until new commands arrive. At interstellar distances, autonomous operation becomes not merely preferable but absolutely mandatory. No human controller can guide a spacecraft through a crisis when the round-trip communication time exceeds years. The spacecraft must contain within itself all the knowledge, capability, and judgment required to handle any situation that might arise during its centuries-long journey. This is a requirement unlike anything current technology achieves. The requirement for comprehensive autonomy introduces its own compounding constraints. Autonomous systems require sophisticated computing capability that consumes energy and adds mass. The computers must be powerful enough to process sensor data, run decision algorithms, execute responses, and monitor outcomes, all without human oversight. This processing demands continuous power that depletes energy reserves throughout the mission. Autonomous decision-making requires programming that anticipates every possible scenario, and this is where the requirement becomes philosophically troubling. No programmer can anticipate every situation a spacecraft might encounter over centuries of operation in environments we have never visited. Conditions will arise that no simulation predicted and no algorithm was designed to address. How should autonomous systems respond to genuinely unanticipated situations? If they follow rigid programming, they may fail to adapt to conditions their designers never imagined. If they have flexibility to improvise, they may make choices that human operators would never approve. The same capability that enables adaptive response also enables catastrophic error, and there is no one to call when the system confronts something entirely outside its training. Autonomous operation must also continue functioning correctly across timescales that exceed the expected lifetime of the computing hardware running the autonomy. Processors degrade, memory corrupts, software may drift through accumulated errors in ways that change behavior subtly over time. An autonomous system that performed flawlessly at launch may make increasingly poor decisions as its cognitive substrate deteriorates. It may not recognize its own declining capability. It may make choices with full confidence that would horrify its designers. The farther you go, the more alone you become, and aloneness activates failure modes that proximity suppresses. A spacecraft near Earth can be monitored, diagnosed, and corrected. A spacecraft light years away operates in functional isolation, regardless of how powerful its communication systems are. The time required for any interaction exceeds useful response timescales. Manufacturing tolerances create another temporal constraint that becomes severe over long missions, revealing how initial conditions compound into system-wide effects. No component is manufactured to exact specification. Every part varies slightly from its design target, falling somewhere within acceptable tolerance ranges. A bearing designed for a specific diameter might actually measure slightly smaller or larger. A resistor rated for a specific value might actually provide slightly more or less resistance. A structural member designed for specific strength might actually be slightly stronger or weaker. These variations are insignificant for short-duration operation. Tolerances are set specifically to ensure that components within acceptable ranges perform adequately under expected conditions. A bearing at the small end of its tolerance range still functions. A resistor at the high end of its tolerance range still works. The variations wash out in overall system performance. But over extended timescales, manufacturing variations accumulate into system-wide effects. A bearing running slightly hot due to dimensional variation will degrade faster than its nominal counterpart. The slight additional friction generates slight additional heat, which slightly accelerates lubricant breakdown, which slightly increases friction further. Over thousands of hours, slight becomes significant. Over millions of hours, significant becomes critical. A seal fitting slightly loosely due to manufacturing variation will leak more quickly than design predictions based on nominal dimensions. The slight additional gap allows slightly more fluid loss, which slightly reduces sealing pressure, which slightly widens the gap. Again, slight effects compound over time into significant effects. A structural member falling at the weak end of its tolerance range will fatigue sooner than nominal predictions suggest. The slight reduction in strength means slightly higher stress for any given load, which slightly accelerates crack initiation, which slightly advances crack propagation. Components that should last centuries based on nominal calculations may fail in decades when manufacturing variations push them toward early failure. Across thousands of components operating for decades or centuries, these manufacturing variations accumulate into system-wide effects that cannot be fully predicted. The spacecraft that was fully functional at launch gradually drifts toward dysfunction as multiple components approach their individual failure thresholds simultaneously. This simultaneous approach to multiple failure points, sometimes called reliability cliff, represents a particularly dangerous failure mode because it can occur suddenly after long periods of apparently normal operation. A spacecraft might operate for 90 years with slowly degrading but still functional systems. Then, within a short interval, multiple systems that had been approaching their limits simultaneously cross those limits. Failure cascades as overloaded backups fail to compensate for failed primaries. As failed systems impose additional loads on surviving systems, as the maintenance debt accumulated over decades comes due all at once, the system that seemed stable was actually balanced on an increasingly precarious edge, invisible until the edge crumbled. Thermal cycling accelerates all these degradation mechanisms through repeated expansion and contraction. As spacecraft rotate through sunlight and shadow, or as equipment cycles between operation and standby, materials expand when warm and contract when cool. Different materials expand at different rates, creating stress at joints where dissimilar materials meet. These stresses flex connections, work fasteners loose, and accumulate fatigue damage in structural elements. A single thermal cycle causes negligible damage. 1,000 cycles cause minor damage. 1,000,000 cycles easily accumulated over decades of operation cause substantial damage that compounds with every other degradation mechanism operating simultaneously. Connections that were tight at launch become loose. Bonds that were solid develop cracks. Structures that were rigid develop flex. This isn't one wall, it's several closing in together. Mechanical wear proceeds alongside electronic degradation. Radiation damage accumulates while manufacturing tolerances compound. Communication delays prevent coordination, while autonomous systems degrade. Thermal cycling stresses every joint and connection, while component lifetimes expire. Each temporal constraint operates independently, following its own physical laws and timescales. Yet all share distance as their primary driver, because distance determines mission duration, and duration determines how severely each temporal constraint affects mission success. The systems designed to mitigate these temporal constraints often create new vulnerabilities rather than resolving underlying challenges. Redundancy adds complexity that increases the number of potential failure modes. More components mean more opportunities for failure, more interactions that can go wrong, more pathways for cascading breakdown. Autonomous operation requires sophisticated software that may contain subtle bugs only revealed under unusual conditions that may not arise for decades, then trigger catastrophic failure in systems that appeared reliable. Radiation-hardened components sacrifice performance for durability, requiring more components to achieve the same capability as standard parts. More components mean more mass, more power consumption, more complexity. The solution to one temporal constraint creates demands that tighten other constraints. Every engineering solution to temporal constraints introduces new constraints that compound with existing ones in ways that resist simple resolution. Maintenance robots have been proposed as solutions to the repair impossibility problem. Autonomous systems could inspect components for wear, diagnose emerging failures, and repair damaged parts without human intervention. Such systems exist in primitive form today. Robotic arms on the space station perform some external maintenance tasks. More sophisticated versions might handle complex repairs entirely independently, but maintenance robots face the same temporal constraints as the systems they are designed to maintain. Their motors wear, their sensors degrade, their software accumulates errors, their bearings fatigue, their seals deteriorate. A maintenance robot operating for a century experiences all the same degradation mechanisms as any other mechanical and electronic system operating for a century. A maintenance system that fails cannot maintain itself. A spacecraft depending on robotic repair inherits the reliability limitations of its repair systems and then must add the repair system's complexity, mass, and failure modes on top of the systems being maintained. the solution may be worse than the problem it attempts to solve. Self-repairing materials represent another proposed solution to temporal degradation. Research has demonstrated materials that can heal cracks through embedded healing agents, restore electrical connections through conductive particles that flow to damaged areas, or regenerate damaged molecular structures through designed chemical processes. These materials genuinely exist and show promise for specific applications, but self-healing processes typically require energy to drive the healing reactions. They operate slowly compared to the timescales of operational demands. They have limited capacity for repeated repair cycles. A material that can heal one crack might not heal 10. A material that heals slowly might not keep pace with continuous radiation damage. And self-healing materials must themselves avoid the degradation that triggers healing. The temporal constraints examined here represent a category of compounding limits independent from but interacting with the energy constraints examined in the previous section. Energy depletion proceeds alongside reliability decay. Power systems lose capacity over time through the same degradation mechanisms that affect all systems, and as power diminishes, the ability to compensate for other failures through active measures diminishes as well. Communication delays affect the ability to manage energy reserves remotely, but this matters little because communication delays are already too long for useful intervention. Radiation damage depletes both biological and electronic resources simultaneously, and shielding against radiation requires energy and mass that create their own constraints. Each category of constraint feeds into others, while simultaneously receiving inputs from distance, the master variable that determines where every individual constraint falls on its severity curve. Time translates distance into duration. Duration translates into accumulated failure probability, accumulated radiation exposure, accumulated mechanical wear, accumulated electronic degradation. The translation is direct, mathematical, and inescapable. Distance does not merely stretch time across a longer interval. Distance weaponizes time against every engineered solution. Every hour of operation becomes another hour for something to break. Every day of exposure becomes another day of radiation damage. Every year of thermal cycling becomes another year of accumulated stress at every joint and connection. Every decade of standby becomes another decade of degradation in backup systems waiting to be needed. The final section examines how all these constraints, energy, time, reliability, communication, radiation, maintenance, converge at interstellar distances. It explores why their simultaneous severity is not coincidental but emerges from fundamental physical relationships, and it considers what this convergence means for the possibility of long-distance travel and humanity's place in a cosmos that permits observation but may prohibit visitation. But even before that convergence is examined explicitly, the pattern has become clear. The universe does not bar long-distance travel with a single gate that sufficient force might breach. It bars travel with many gates that all close together, each one feeding into others, each one tightened by the same distance that tightens all the rest. Time is one set of those gates, and time alone before considering its interactions with energy, communication, and all other constraints already presents barriers that multiply rather than add as distance increases. The constraints examined in previous sections, energy demands that spiral beyond civilization-scale resources, temporal decay that transforms every system into a countdown toward failure, communication breakdown that isolates travelers from any possibility of guidance, reliability dissolution that guarantees eventual collapse of even the most robust designs, might each yield to focused engineering effort if encountered in isolation. History demonstrates that humanity can solve extraordinary problems when sufficient resources and ingenuity are directed at singular challenges. We split the atom, we reached the moon, we decoded the genome, we built thinking machines. Each accomplishment required overcoming obstacles that seemed insurmountable to previous generations. Each proved that determined intelligence can breach barriers that appeared permanent, but the universe does not present the constraints of long-distance travel in isolation. It presents them together, simultaneously, at approximately the same distance threshold. This convergence transforms a collection of difficult problems into something qualitatively different. A trap where solving any individual problem merely illuminates the others waiting behind it. The convergence is not coincidental. It is not an accident of our current technological limitations that future breakthroughs will eventually overcome. It emerges from the fundamental structure of physical law applied to travel across cosmic distances. Energy requirements increase with distance because propulsion demands energy proportional to velocity change, and achieving useful speeds toward distant targets requires velocity changes far exceeding anything humanity has accomplished. The relationship is not merely linear, but compounds through the mass-energy interactions that govern all propulsion. Time constraints increase with distance because travel time grows at least linearly with distance, and typically faster when acceleration and deceleration phases are considered, and because the speed of light imposes an absolute ceiling that no propulsion system can exceed. Reliability constraints increase with distance because operational duration determines how severely component failure probabilities accumulate, and longer distances mean longer durations, mean more accumulated probability of failure. Communication constraints increase with distance because signal strength diminishes according to the geometry of expanding spheres, while light travel time grows according to the unchangeable speed of electromagnetic propagation. Each constraint follows its own physical relationship to distance. Each emerges from different branches of physics: thermodynamics, relativity, probability theory, electromagnetic theory. Each has been studied by different communities of scientists using different mathematical frameworks. Yet all share distance as their driving variable. All respond to the same underlying cause, and all approach critical severity at approximately the same range. This shared driver creates the compounding effect that makes long-distance travel so fundamentally different from the engineering challenges humanity has previously overcome. The constraints do not take turns becoming severe, presenting themselves sequentially in a queue that patience and persistence might eventually clear. They become severe together, at approximately the same distance range, because they all respond to the same underlying variable with relationships that happen to produce similar thresholds. The distance at which energy requirements become civilization-scale challenges roughly coincides with the distance at which mission durations exceed component lifetimes. Both roughly coincide with the distance at which communication delays prevent meaningful coordination. All three roughly coincide with the distance at which radiation exposure accumulates beyond any practical shielding capacity. This clustering is not arbitrary. It reflects deep relationships between the speed of light, the energy content of matter, the reliability of physical systems, and the geometry of three-dimensional space. The speed of light determines both how quickly you can travel and how quickly you can communicate. It sets the ultimate ceiling on propulsion while simultaneously setting the floor on communication delay. Faster travel reduces communication delay because you arrive sooner, but faster travel requires more energy. The same constant appears in both equations, linking constraints that might otherwise be independent. The energy content of matter determines both propulsion limits and power generation capabilities. The same atomic and nuclear binding energies that limit how much fuel can do also limit how much power can be generated to run spacecraft systems. You cannot escape one limitation by exploiting the other because they derive from the same underlying physics. The reliability of physical systems depends on the same physical laws: thermodynamics, quantum mechanics, materials science that govern energy and time constraints. Materials degrade because thermodynamics requires entropy to increase. Electronics fail because quantum mechanics permits random events that corrupt stored information. Structures fatigue because materials science describes how crystalline structures accumulate damage under stress. These are not separate limitations, but different expressions of the same underlying reality. This is where all the limits stack together at once. At interstellar distances, You face energy requirements so vast that fueling a single mission would require resources exceeding global civilization's annual energy production multiplied many times over. Current human energy consumption totals roughly 600 exajoules per year. Accelerating even a modest spacecraft to useful interstellar velocities would require energies measured in thousands of exajoules, concentrated into propulsion systems, rather than distributed across civilization's diverse needs. You face mission durations so long that every component would pass through multiple expected lifetimes. A journey to the nearest star at velocities achievable with any realistic near-future technology would span decades at minimum. Centuries more likely. No manufactured system has demonstrated reliability across such timescales. The longest operating spacecraft have functioned for roughly 50 years, with substantial degradation already evident. You face communication delays so extreme that no meaningful coordination between spacecraft and controllers would be possible. Messages would take years in each direction. By the time a problem report reached Earth, the situation would have evolved beyond recognition. By the time any response arrived at the spacecraft, the original problem would have either resolved itself or cascaded into catastrophe. You face radiation exposure so cumulative that both biological and electronic systems would sustain damage beyond any reasonable shielding capacity. Decades of exposure to galactic cosmic rays would accumulate doses that no biological repair mechanism could address, and no electronic hardening could withstand. Shielding sufficient to reduce exposure to acceptable levels would mass so much that propulsion requirements would spiral beyond any reasonable limit. You face maintenance impossibilities so complete that gradual degradation could not be addressed by any repair mechanism. Components would wear, connections would loosen, materials would fatigue, and nothing could be done about it. No spare parts could be carried in sufficient quantity. No repair capability could match the breadth of potential failures. No monitoring system could detect every mode of degradation. Each constraint alone might be addressed through extraordinary measures, given sufficient resources and determination focused on that single problem. Humanity could conceivably develop propulsion systems capable of achieving interstellar velocities if energy were the only challenge. We might apply our entire civilization's energy budget to a single mission. We might develop propulsion concepts that approach theoretical efficiency limits. We might accept the resource commitment as worthwhile despite its enormity. We could possibly engineer systems reliable enough to operate for centuries if reliability were the only concern. We might develop materials that degrade more slowly. We might design architectures with unprecedented redundancy. We might accept spacecraft massing many times what minimal designs would require, carrying enough backup systems to survive any plausible failure sequence. We might find ways to protect against cumulative radiation damage if exposure were the only variable. We might develop active shielding using superconducting magnets powered by onboard reactors. We might engineer radiation-resistant biology through genetic modification. We might accept reduced crew lifespans as acceptable cost for reaching distant destinations. But we cannot simultaneously solve all these challenges because solutions to each create demands on others that tighten rather than loosen the overall constraint system. This is the crux of convergence. This is why the problem is not merely difficult but may be fundamentally different from engineering challenges that focused effort can eventually overcome. Consider what solving the propulsion constraint actually requires in practice. To achieve meaningful interstellar velocities fast enough that journeys span decades rather than millennia, spacecraft must accelerate to substantial fractions of light speed. Even modest fractions, say 10% of light speed, represent velocities hundreds of times greater than any spacecraft has achieved. The energy required for such acceleration, even with theoretically perfect propulsion efficiency, approaches the energy equivalent of the spacecraft's entire mass as velocity climbs toward relativistic territory. Faster travel times would reduce exposure duration and ease reliability demands. One less decade of operation means one less decade of component degradation. one less decade of radiation accumulation, but faster travel requires even greater velocities and proportionally greater energy. The relief provided to reliability and radiation constraints comes at enormous cost to energy constraints, and acquiring, storing, and deploying such energy requires systems that add mass reactors, fuel tanks, thermal management equipment, which increases energy requirements, which adds more mass. The propulsion solution expands rather than contracts the problem when examined in full context. Now consider what solving the reliability constraint actually requires. To ensure system function across century-long missions, spacecraft would need either perfect component reliability, which violates fundamental physical principles that guarantee eventual failure of any physical system, or comprehensive redundancy, with replacement capacity sufficient to cover any failure sequence. But adding redundancy adds mass that increases propulsion requirements. It adds complexity that creates new failure modes. More components mean more opportunities for malfunction. It adds energy consumption that depletes reserves faster, potentially extending mission duration if energy must be rationed. The reliability solution transfers difficulty to other constraints rather than reducing total constraint severity. Similar logic applies to every proposed solution when examined honestly. Better radiation shielding adds mass that worsens propulsion constraints. More powerful communication systems require more energy that worsens power generation constraints. Extended life support capacity adds both mass and energy demands that worsen multiple constraints simultaneously. More sophisticated autonomous systems add complexity that increases failure modes while requiring more processing power that increases energy consumption. Each engineering solution applied to one constraint imposes costs on others that maintain or increase overall constraint severity. Pulling on any thread tightens others. This coupling is not a failure of imagination or a temporary limitation of current technology. It reflects the underlying physical relationships that connect energy, time, mass, and reliability through shared dependence on fundamental constants and laws. This constraint transfer effect demonstrates why no single technological breakthrough can solve the problem of long-distance travel, regardless of how revolutionary that breakthrough might be. A propulsion breakthrough that reduces fuel requirements by a factor of 10 would be genuinely extraordinary. It would represent the kind of advance that transforms entire fields and enables capabilities previously relegated to science fiction. It would extend humanity's practical reach substantially within our solar system, making missions that are currently prohibitive become feasible. But it would not solve interstellar travel because the other constraints would still converge at approximately the same distance threshold. Better propulsion buys faster travel times, but faster travel still requires decades to nearest stars with any physically realistic propulsion concept. During those decades, reliability decay still accumulates according to the same probability mathematics. Radiation exposure still damages systems according to the same physics of particle interaction. Communication delays still prevent coordination, according to the same geometry of light propagation through space. The breakthrough that solved propulsion would merely reveal more clearly the constraints that propulsion was obscuring. The energy barrier, once crossed, would show the time barrier standing immediately behind it. Cross the time barrier through some further miracle, and the reliability barrier would appear. The barriers do not form a single wall. They form a series of walls so close together that breaching one leaves you immediately facing the next. The universe constrains long-distance travel, not through any single insurmountable barrier, but through the convergence of multiple barriers at approximately the same distance. Overcoming any one barrier does not eliminate the others. It merely reveals them more clearly, standing alongside the newly crossed threshold, still barring passage. The convergence creates a zone where all paths close simultaneously, where every direction of advance runs into some limit that distance has already activated. This convergence creates what might be called a complexity trap that offers no obvious escape. Simple spacecraft with minimal systems might avoid some complexity-related failures, but simple spacecraft would lack the capability to complete long-duration missions. They could not carry sufficient fuel, generate sufficient power, maintain adequate life support, provide adequate shielding, or perform adequate autonomous operations. Simplicity trades capability for reliability in ways that leave missions unable to succeed even if systems function perfectly. Complex spacecraft with comprehensive capabilities could potentially handle the challenges of interstellar travel if they functioned as designed. They could carry extensive fuel reserves, generate abundant power, maintain sophisticated life support, provide comprehensive shielding, and perform advanced autonomous operations. But complex spacecraft face compounding failure probabilities from their many interacting systems. More capability means more components mean more failure modes. More failure modes mean higher probability of catastrophic breakdown over extended operations. Neither simplicity nor complexity provides an escape route from the convergence zone, where all constraints become severe together. Simple designs fail by lacking capability. Complex designs fail by accumulating failures. The optimal design point that balances capability against reliability exists, but at interstellar distances that optimal point still falls short of mission success requirements. The constraints have closed tight enough that no design thread passes through all the needles simultaneously. Some proposed solutions attempt to sidestep particular constraints rather than overcoming them directly, accepting one category of difficulty in exchange for relief from another. Generation ships, where multiple human lifetimes pass during the journey, accept extreme mission durations rather than trying to minimize them. If the journey takes 1,000 years, let it take 1,000 years. Build a ship large enough to sustain a population across generations. Accept that the crew who arrives will be descendants of the crew who departed, separated by dozens of generations from anyone who knew Earth directly. Suspended animation concepts try to reduce life support requirements by keeping crew in metabolically inactive states throughout most of the journey. If humans require resources only when conscious and active, reduce the time they spend conscious and active to brief intervals while they sleep through centuries of transit. This transforms life support from an ongoing challenge into a preservation challenge, keeping bodies intact through mechanisms not yet developed. Robotic probes eliminate biological constraints entirely by removing biology from the mission. If humans are too fragile, too resource-intensive, too vulnerable to radiation and time, send machines instead. Machines do not need food, water, or breathable atmosphere. Machines can be built with radiation-hardened components that would be impossible to incorporate into biological systems. Digital uploads of human consciousness speculate about eliminating both biological and mechanical constraints through information-based travel. If consciousness could be transferred to computational substrates, those substrates might be more robust than neurons. If consciousness could be transmitted as information rather than transported as matter, it might be sent at light speed rather than at the plodding velocities that matter achieves. These concepts venture deep into speculation about consciousness, identity, and the nature of experience. Each proposed approach does genuinely address some constraints. Generation ships do eliminate the requirement that individual humans survive complete journeys. They replace that requirement with the requirement that populations survive complete journeys. Robotic probes do remove life support requirements. They replace them with autonomous operation requirements that may be equally severe. Suspended animation does reduce resource consumption during transit. It requires preservation technologies that do not exist and may not be achievable. Digital consciousness does offer paths around physical barriers. It requires understanding of mind that may not be possible, but each approach also activates new constraints or transfers difficulty to categories that were previously manageable. Generation ships require closed ecological systems that must function for millennia, a reliability challenge far exceeding any current technology by factors so large they may represent different categories of problem entirely. Ecosystems are complex, interdependent, sensitive to perturbation. No closed ecosystem has been demonstrated to function for more than brief periods without external inputs and corrections. Robotic probes must operate autonomously for centuries, while maintaining function and purpose in the absence of human guidance. They must make decisions their designers cannot anticipate about situations their designers cannot foresee. They must remain committed to goals established at launch despite whatever conditions they encounter and whatever internal degradation they experience. Autonomy at this level has never been demonstrated and involves philosophical questions about purpose and motivation that engineering cannot fully address. Suspended animation requires perfect preservation of biological systems across timescales, exceeding any demonstrated capability. The longest successful preservation of complex biological systems measures in hours for some organs, decades for simple samples like frozen embryos. Centuries of suspension would require technologies that maintain cellular integrity without metabolic function, prevent ice crystal damage that destroys tissue structure, and permit restart of biological processes after interruptions longer than any organism has experienced. Digital consciousness transfer requires technologies that currently exist only in speculation, building on understanding of mind and identity that philosophy has debated for millennia without resolution. Even if consciousness could be transferred to computational substrates itself, an enormous assumption, those substrates would face their own reliability and energy constraints. Computers degrade, software corrupts. Digital systems are not exempt from physics. The farther you go, the more systems fail at once, regardless of what systems you choose or how you configure them. Generation ships face ecological collapse. Robotic probes face purposelessness and degradation. Suspended biology faces preservation failure. Digital minds face substrate decay. The specific failure modes differ, but the underlying pattern remains. Distance activates constraints that peak together, and no architectural choice escapes the convergent zone. The conclusion emerges with uncomfortable clarity from examining every proposed pathway and finding each blocked by its own category of convergence. Long-distance travel fails, not because the universe presents an insurmountable wall that some future technology might breach. It fails because the universe presents too many walls closing in at the same time. The energy wall and the time wall and the reliability wall and the communication wall and the radiation wall and the maintenance wall all converge at approximately the same distance threshold. Climbing one reveals that others have moved closer. Tunneling through one finds others immediately behind it. No single direction of advance escapes the convergent zone, where constraints compound rather than add. This convergence may represent a fundamental feature of physical reality, rather than a temporary limitation of current understanding. The physical laws that create each individual constraint are well established and show no signs of revision despite centuries of scientific investigation. The relationships between those laws that produce convergence emerge from mathematics rather than engineering. The distance at which constraints converge is determined by constants built into the structure of space-time itself. What does this convergence mean for humanity's relationship with the cosmos, for our understanding of where we stand and what possibilities remain open to us? It means that the universe we can observe may not be the universe we can visit. Light travels freely across cosmic distances, carrying information about stars, galaxies, and structures spanning billions of light years. Photons cross the void without degradation, without fuel consumption, without the accumulated failures that doom matter-based travel. Through observation, humanity has learned about the scale and structure of existence from subatomic particles to cosmic superclusters. We have mapped galaxies billions of light years distant. We have detected the cosmic microwave background radiation from the earliest visible epoch of cosmic history. We have inferred the existence of dark matter and dark energy that dominate cosmic contents despite remaining invisible to direct observation. But observation does not imply access. The same physical laws that permit photons to cross cosmic voids without impediment also constrain matter, energy, and information in ways that may permanently limit travel. Photons have no mass, require no fuel, accumulate no degradation, and travel at the universal speed limit without effort. Matter has mass that requires energy to accelerate, fuel that depletes with use, components that degrade over time, and velocities that can only approach but never reach light speed. The universe opens itself to examination while closing itself to exploration. It means that distance functions as a fundamental isolation mechanism built into physical law, separating what the universe permits to be seen from what it permits to be reached. Life might evolve on countless worlds throughout the cosmos. The same chemistry that produced life on Earth operates throughout the observable universe, and the conditions that permitted Earth's biology appear common among the countless planetary systems now being discovered. Civilizations might rise on those worlds and contemplate their surroundings just as humanity contemplates ours. They might develop technology, ask questions about their place in existence, wonder whether they are alone. But the distance between worlds may ensure that most civilizations develop, flourish, and decline without ever making contact with others, regardless of how numerous those others might be. The cosmos might teem with life yet remain functionally empty, as each island of consciousness remains isolated by distances that compound too many constraints for any technology to overcome. The silence we observe when we search for signs of extraterrestrial intelligence might not indicate absence of intelligence. It might indicate the same convergence we face, the same compounding constraints that close around every attempt to communicate across cosmic distances. It means that some problems might be permanently unsolvable, not because solutions are impossible to conceive, not because we lack imagination or determination, but because multiple partial solutions cannot be combined into complete solutions. The engineering genius of future generations may dramatically improve propulsion efficiency beyond anything we can currently imagine. They may develop radiation shielding that reduces exposure by orders of magnitude. They may create systems so reliable that component lifetimes extend far beyond current expectations. They may design autonomous operations so sophisticated that human guidance becomes unnecessary. Each improvement would represent genuine progress. Each would extend humanity's practical reach. Each would make possible missions that current technology cannot achieve. But progress on all fronts simultaneously sufficient to cross the convergence zone may exceed what physical law permits. The constraints are coupled. The improvements in one domain create demands in others. The convergent zone moves but does not disappear as technology advances because the constraints are connected through underlying physics that no technology can alter. This interpretation represents one possibility, consistent with current understanding of physical law. The constraints examined here are real and measured. The relationships between them emerge from established physics. The convergence is not speculation but calculation. But projections about future technology involve uncertainty that honest analysis must acknowledge. Perhaps some yet undiscovered physical principle will provide capabilities that sidestep current constraints entirely. Physics has surprised humanity before with discoveries that transformed understanding, relativity, and quantum mechanics upended classical certainties within decades. Perhaps similar surprises await that will render current constraint analysis obsolete. Perhaps the convergent zone is not as absolute as current analysis suggests. Perhaps creative approaches not yet conceived will find paths through barriers that seem impenetrable today. Human ingenuity has repeatedly exceeded prior expectations of the possible. Perhaps interstellar travel will eventually join the list of impossible things that determined effort achieved. But the honest assessment of current knowledge provides little comfort for those who dream of traveling between stars. The physics is well established. The constraints are measured. The convergence is calculated. The universe is constructed not a gate that might someday be opened with the right key, but a trap where many gates close together, each one requiring its own key, all keys needed simultaneously. Humanity sits on a small planet, orbiting an ordinary star in the outer reaches of an average galaxy. Our sun is one of perhaps 400 billion stars in a galaxy that is itself one of perhaps 2 trillion galaxies scattered across the observable cosmos. We occupy no privileged position. We possess no special exemption from physical law. We are ordinary matter organized into remarkable patterns that have developed the capacity to contemplate the cosmos from which that matter emerged. We have developed the capability to observe cosmic structures spanning billions of light years. We have built instruments that detect light that has traveled for billions of years before reaching our detectors. We have achieved the ability to send spacecraft to other worlds within our solar system. We have landed instruments on Mars, orbited Saturn, dispatched probes toward interstellar space. We have begun the process of understanding our place in a universe far vaster than our ancestors imagined. These accomplishments represent genuine triumphs of curiosity, intelligence, and determination. They demonstrate what humanity can achieve when it focuses its capabilities on understanding and exploring. They suggest that our reach may extend further still as technology advances and knowledge accumulates. But understanding our place may require accepting limitations that intelligence and determination cannot overcome. The same physical laws that enabled our emergence, that built atoms from particles, that forged heavy elements in stellar cores, that organized matter into the complexity that eventually became biology, and then consciousness also constrain our reach. The cosmos that produced beings capable of contemplating distances may permanently deny those beings the ability to traverse them. We can see farther than we can ever travel. We can understand more than we can ever experience directly. We occupy a cosmic observation post with windows on infinities we can never explore. This is not a failure of human potential. It is not an indictment of our efforts or a prediction that we should stop trying. It is a feature of physical reality as fundamental as the existence of matter and energy themselves. The universe was not designed for traversal by small beings bound to single worlds. It was not designed at all. It simply operates on scales where even light, the fastest thing that can possibly exist, requires years to cross between neighboring stars and billions of years to cross the observable cosmos. Matter, bound by different rules than light, faces even more severe constraints. We are made of matter. Our spacecraft are made of matter. Our energy sources are made of matter. And matter cannot escape the physics that governs matter, regardless of how cleverly we arrange it. The compounding limits that close around long-distance travel represent not hostility but indifference. The natural operation of physical law applied to movement across cosmic space. The universe does not care whether we travel between stars. It does not prevent us through malice. It simply embodies relationships between energy and mass, time and distance, reliability and complexity that happen to produce convergent constraints at distances beyond our solar system. Understanding this indifference may represent a form of maturity for a species recently emerged from planetary parochialism. For most of human history, we believed Earth occupied the center of existence, with the cosmos arranged around us for our observation and habitation. We have progressively abandoned those comforting illusions. We have learned that Earth is not the center of the solar system. We have learned that the solar system is not the center of the galaxy. We have learned that our galaxy is not the center of the universe. We have learned that the universe has no center at all. Now, we may be learning something equally profound, that our ability to reach extends only to a tiny fraction of what we can see. Observation is not the same as access. Knowledge is not the same as experience. The cosmos opens itself to examination through the light it freely provides while closing itself to exploration through the constraints that govern matter and energy. The barriers described throughout this examination: energy requirements that exceed civilization-scale resources, time constraints that exceed component lifetimes, reliability limits that guarantee eventual failure, communication delays that prevent coordination, radiation exposure that damages all known systems, maintenance impossibilities that prevent repair might someday be characterized more precisely as our understanding advances. The convergent zone might be mapped with greater accuracy as measurements improve. The relationships between constraints might be understood more deeply as physics progresses, but the fundamental insight appears robust. The universe makes long-distance travel almost impossible, not by presenting a single wall that sufficient force might breach, but by presenting many walls that close together, each one manageable alone. All of them together, forming a barrier that may stand forever. Not one constraint but many. Not one threshold but convergent thresholds. Not one problem to solve but coupled problems that transfer difficulty rather than eliminating it. You have followed this examination from individual constraints through their interactions to their convergence. You have seen how energy requirements compound with time requirements, how time requirements compound with reliability limits, how reliability limits compound with communication constraints, how all constraints share distance as their common driver. You have seen why solving any one constraint does not solve the overall problem, why the gates form not a sequence, but a cluster that must be passed simultaneously. You are processing these ideas on one planet orbiting one star among 400 billion in a galaxy that spans 100,000 light-years. Beyond that galaxy lie 2 trillion others, scattered across a cosmos 93 billion light-years wide. The light from those distant structures reaches us freely, carrying information about wonders that exceed any imagination. Stellar nurseries where new suns ignite, black holes that consume everything that approaches, galaxies colliding across timescales longer than the history of life on Earth. But the matter that constitutes us, the atoms that form our bodies, the neurons that generate our thoughts, the hands that built our instruments that matter, may be confined to a tiny sphere centered on our small world. We are bounded not by a wall we might someday breach with sufficient technology and determination, but by the compound weight of physical constraints that all peak together at the threshold of interstellar distance. This is why the universe makes long-distance travel almost impossible. Not one barrier, but many. Not a sequence of obstacles to be overcome one after another, but a convergence of obstacles that close together simultaneously. Not a lock awaiting the right key, but a trap, where every exit narrows at the same moment, leaving no path through the gaps between them. The cosmos permits observation while prohibiting visitation. It shows us infinities while confining us to our corner. It provides windows on wonders we cannot touch. The stars will remain distant. The constraints will remain coupled. The convergence will remain regardless of how technology advances, because the physics that links energy to mass, time to distance, and reliability to complexity cannot be overridden by cleverness alone. But we remain curious, determined, capable of understanding even limitations we cannot transcend. We are the universe becoming aware of itself matter, contemplating its own constraints, consciousness examining the boundaries of its possible experience. That examination cannot carry us to the stars we study from afar, but perhaps it carries us somewhere equally profound, toward acceptance of our place in a cosmos that did not arrange itself for our convenience, toward wisdom about the difference between what we can know and what we can reach. In a universe indifferent to our aspirations, understanding may be the greatest journey available to matter that has learned to contemplate its own existence. And that journey, the journey of comprehension, of honest reckoning with physical law, of finding meaning within limits rather than beyond them, that journey we have already begun.